All right, let's take a second to look at limiting reactant. Now, this is problem number 11 from our last discussion worksheet. Here we're considering, as you can see, the reaction between silicon dioxide, carbon, and that forms silicon carbide and carbon monoxide. All right, and let's read the prompt. Silicon carbide, SiC, is one of the hardest substances known, making it valuable as an abrasive. It's made by the high temperature reaction of silicon dioxide with carbon. Now, let's get to the actual problem. Determine the limiting reagent when a mixture of this amount, 5.00 times 10 to the third grams of silicon dioxide and 5.00 times 10 to the third grams of carbon react. What is the maximum number of grams of silicon carbide that can form? So to get the answer to this problem, we first need to find which of these species, either silicon dioxide or carbon, is a limiting reactant. And to do that, there are a few ways to do this. I know of two solid ways to do this. I'm going to show one, and one way to do this is to figure out the amount of moles of this and see how many moles of the product you can make. And then we will find out how many moles we have of this and see how many moles of product that makes. Okay, and to do that, we're just going to do some dimensional analysis to figure that out. So let's see what we're starting with again. 5.00 times 10 to the third grams of silicon dioxide. So let's start with that. 5.00, 10 to the third grams, silicon dioxide. And if we're going to do dimensional analysis, I've talked about this, put the thing you want to cancel out at the bottom. So if we know we need moles and we have grams, we need the molecular weight, right? And if we're going to put the thing we want to cancel out at the bottom, put the rest of it up there, the other unit up there, and now put the number by the grams, right, from molecular weight, because it's so many grams per mole. How many grams per mole of silicon dioxide? Add them up, the mass of silicon and the mass of 2 oxygen atoms. There we go, 60.085. And now we're in moles, right? We're in moles of what? SiO2. Let's continue this dimensional analysis. And now we'll go over, now we need to do a molar conversion because we want to get to moles of SiC. Now we need to do a molar conversion. But what I forget to do to this point, what do I need to do? I need to balance the reaction, right? We're going to need some kind of molar conversion here. And look at me, I haven't balanced it yet. So let's balance it. Let's just try. I like to start with the easy molecule. And this isn't necessarily a balancing, this isn't a balancing video, okay? So I'm sorry, I'm kind of getting right to the point here. All right, if we have one Si over there on the right, we have to have one, right? Okay, I'm gonna leave the carbon open for now. That one SiO2 gave us 2 oxygen, so we would need at least 2 there. We have one Si there. On the left, we have one Si over there. And let's just fill the rest of the carbons. So here we have 1 carbon, there are 2 carbons, that's 3. I think that works. Now that we have those molar ratios, we can finish this out. Let's go back down here. You'll want to work that into your habits to do that very first in the exam, okay? So now we need the molar ratio. And again, the thing you want to cancel out, if you're ever wondering what do I put at top of bottom, remember to put the thing you want to cancel out at the bottom. And you can do that before you even consider the numbers, right? And now we'll put the moles of the thing we want on the top. And that was going to be SiC. There we go. Now let's just fill in the molar ratio. So for how many SiO2 do we have for every SiC? And we'll just fill in those numbers. And it looks like it's 1 and 1. And we'll get some molar value out of that. So we go 5,000 divided by 60.085. And make sure you hit enter after you do every calculation in your dimensional analysis. It helps. Okay, so I got 83.22 moles. Now let's use the other reagent and see what we get with that. Now we're done figuring out how many moles of product we got with this silicon dioxide. Now we're going to check with carbon. So they also told us up here that we had 5,000 grams of carbon. We don't have to do too much math to figure out the molecular weight of carbon. So put the thing you want to cancel out at the bottom. And we use molecular weight to go from grams to moles, right? We're safe to use 12 grams a mole for carbon right now. Now we're in moles carbon. We need to get to moles SiC. So now we need to do a molar conversion. And then put the thing you want to cancel out at the bottom. And here we're going from carbon, that's what we want to cancel out, to SiC. And we'll see how many moles that is. Sorry, it's so cramped. I'll try and put a border here. So we don't mistake as those pieces of information is being related. Okay. So now let's fill in the molar conversion values. And we just pull those from the equation like we did before. So how many SiC for every C? So look, 1 SiC for every 3 C. So that just has to be divided by 3. Let's do it. Let's see how many moles we get. 5,000 divided by 12, enter. Divided by 3, enter. And I got 138.89 moles carbon. Okay, you could take those both to grams if you wanted, but that wouldn't make sense because we only need to take 1 to grams, and that's the limiting reaction. So now we have 2 different sets of moles. We found in one, oh, I put C, I'm sorry. There we go, SiC. In one case, we formed 83.22 moles SiC, and in the other case, we formed 138.89 moles of product. So the thing that forms less product is your limiting reagent. That's the thing that will run out first. So this one over here, limiting reagent equals what? Which formed less product? I would say it was the silicon dioxide. And again, that was because it formed less moles of product. Let's get that up there. Okay. So now that we know which of these is the limiting reagent, let's convert those moles SiC to grams, because that's what the question's asking for. How many grams can be formed maximum? So you don't have to round that problem yet. You could have just taken the dimensional analysis here, this divided by that, and that gave us 83.22. Then you could continue with that number and convert it to grams. So you don't have to round that yet. If you wanted to punch it back in your calculator, that would be more accurate, so you're not rounding. I've just rounded that number for simplicity for instructional purposes here. That makes it go a lot clearer. Okay, and it actually helps to kind of write these numbers. Why I do that is it helps to write these numbers, and so you can compare like that you got that same amount of moles. It helps troubleshoot your steps. But just know that you don't round till the end, right? We've talked about that. So 83.22 moles silicon carbide. Let's convert that to see how many grams that would be. How do we do that? If you forget, just put the thing you want to cancel out at the bottom. If you forget if you need to multiply or divide by the molecular weight, piece of cake. Now write the grams there for SiC. So if silicon is 20.085 grams per mole and carbon is 12, just add those together. I think I can do that in my head. Or actually, sorry, silicon is 28.085 grams per mole. So that plus 12 will be 40. My apologies. For every mole. Okay, just multiply those together. We should have our grams. So 83.22 and times 40.85 delta. Oh, sorry, 40.085. And we get a big number. So write it all out. And look how many grams we get. So what is that number? That's how many grams of product formed, right? And now your job is to figure out how many significant figures are appropriate for this. Okay. So that's how much product was formed. Now we have one more question. And you should be familiar with how to do this, definitely, because this is definitely something you can expect to get asked about. How many grams of the excess reactant remain after the reaction is complete? Let's talk about it in words. What does that mean? How many grams of the excess reactant? The excess reactant. So if the limiting reagent was silicon dioxide, the excess reagent is the other one. In this case, it was carbon. So we had to use some amount of carbon to react with silicon dioxide, right? Now, so what we need to do is find out the total moles of carbon, find out the total moles of carbon, subtract out the amount of carbon moles that reacted with the silicon dioxide limiting reagent, subtract that out, and then you get what's left over. So let's first figure out how much carbon we used by doing dimensional analysis, starting with the grams of the limiting reagent. I'm just going shorthanding. It was 5,000 grams of SiO2, the limiting reagent, converted to moles. We know how to do that already. There we go. Now we're in moles, and it's okay to say it out loud. We're in moles of SiO2. SiO2, you see that? Now we're in moles of SiO2. Now we need to do a molar conversion, right? To get into carbon. So we can look at our reaction. What's the proportions we need to use here? So for every 3 carbon, we have 1 SiO2. So that's what we'll use. If you forget what you need to do, just first write out the moles and then put the thing you want to cancel out on the bottom. And that tells you where the other thing goes, right? And then just fill out the numbers. That was 3 and that was 1. And now we're in what? Moles carbon. So you decide how you want to do it. The final answer was in grams, so we can just keep going to grams here. So how do we get to grams? If we're in moles carbon now, we're in moles carbon used. How many grams? Let's just say that was times. If we're in moles, we need to cancel out moles, so that's going to go at the bottom. Moles is going to go on the bottom, grams on top, so 12 times 12. And that's how many grams carbon were used in the reaction. So let's get that number, and then we're just going to subtract it out from the total to get the excess amount. So 5,000 divided by 60.085, and I hit enter, or equals, whatever, and then times 3, enter, and then times 12, enter. And of course, there are times you can take shortcuts to that, but I'm just trying to build a good habit of hitting enter on each step of the dimensional analysis. You don't always have to if it's multiplication. You can do some shortcuts, but I've found it ends up saving time if you just do it one at a time. This equal to what I got was 2,995.756012. Of course, you'll have to round that, right? But what are we in? We're in grams. If you just follow the dimensional analysis, we're in grams, right? So what does that number represent? That was the grams, used of carbon that we got from the limiting reagent. So now we just subtract that from the total amount of carbon, which was what they told us in the problem. It was 5,000 grams, right? So now this number we just got, we just take that away from 5,000 grams, and that's our excess. I'm going to write a little line so it's kind of by itself. I'll draw it in blue. So now we have the total amount, which they told us in the problem, 5,000 grams, and minus this number we just got. And just don't round it till the end, okay? 756,012 grams. Let's see what we get. So I got 2004. 2004. And remember, the most sig figs it could even be, it had this 5.00 number up here. Remember that? So I got, it's going to be around 2004, which when you round that is what, like 2.00 times 10 to the 3 grams. If you're going to round that. There we go. So that's how you do a problem like that. And please get familiar. Let that be a casual skill to you, please. And you just may have to do a few of them, or like 10 of these kinds of problems before you get smooth at it. But essentially, you notice we just figured out how much product was formed from both different species in the reactant, right? And we found which formed the lowest amount of product, and then we went with that one as a limiting reagent, that species. And then we were able to calculate the amount of excess by using the proper molar ratios of carbon to figure out how many moles of carbon were consumed in the reaction, and we deducted those moles of carbon, or those grams of carbon, from the total amount of carbon. So good luck. As always, don't be afraid to email me if you have any questions for class. So take care, everyone.